Welcome to V3d. In the last lecture, we proved a theorem about the distance of a linear code in terms of a PCM for that code. A corollary of the theorem told us that the distance of a linear code is equal to the minimum number of columns of a PCM for that code that are linearly dependent. In this lecture, I'll introduce you to the Hamming codes, which are single error correcting codes. For each finite field GFQ, there is an infinite family of Hamming codes over that finite field. We'll also see a simple decoding algorithm for all single error correcting codes. Hamming codes were discovered by Richard Hamming in 1950. These codes generalized the example we did at the end of the last lecture, where we constructed a PCM for a 743 binary code. Recall that a PCM for such a code must be a 3 by 7 matrix. Since its distance is 3 and it's a binary code, the columns of the PCM must be non-zero and distinct. And since there are only 7 non-zero vectors of length 3 over Z2, we had no choice but to include each of the 7 non-zero binary vectors of length 3 exactly once as a column of H. The only choice we really have is in the ordering of these columns, and a different ordering would give us an equivalent code to the one we constructed. I'll next define the general class of Hamming codes. A Hamming code of order R over GFQ is an NK linear code over GFQ, where the length of the code is q to the r minus 1 over q minus 1, and the dimension is n minus r. And a PCM for the Hamming code is a matrix HR, which has dimensions r by n, and whose columns are non-zero, and no two of which are scalar multiples of each other. Note that the length and dimension of a Hamming code are determined by their order R and the alphabet size Q. Note also that the conditions on the columns of the PCM that they're non-zero and no two are scalar multiples of each other guarantees that the Hamming code has distance at least 3. In fact, we'll see that the distance is exactly 3. So all Hamming codes of order R over GFQ are single error correcting codes. Let's take a look at an example. We'll construct a parity check matrix for a Hamming code of order 3 over Z3. So here, the alphabet size is 3, the order is 3. The length of the code should be n equals 13, its dimension is 10, and the distance should be at least 3. A PCM for such a Hamming code should be a 3 by 13 matrix. Its columns are vectors of length 3 over Z3. There are 27 such vectors. We can't use the 0 vector as a column, which leaves 26 non-zero vectors to choose from. Also, no two columns of H can be scalar multiples of each other. Once we've chosen one of the 26 non-zero vectors as a column of H, we can't use twice that vector or that vector itself as another column. And so there's only 13 choices for the columns of H3, up to scalar multiplication by 2. So, I'll arbitrarily choose the first column to be 1, 0, 0. This means I can't use the vector 1, 0, 0 again, nor the vector 2, 0, 0 as another column in the remainder of the matrix. Next, I'll choose 0, 1, 0, then 0, 0, 1, then 1, 1, 0, which means I can't use 1, 1, 0 again, nor can I use 2, 2, 0, and so on to get 13 columns. The only choices I really had were in the arrangement of these columns, and also choosing a non-zero vector or twice that vector as a column. Note that the matrix H3 has rank 3. Its columns are non-zero, and no two are scalar multiples of each other. Also, the fourth column of H is the sum of the first two columns. So the smallest number of columns of H3 that are linearly dependent over Z3 is 3. Hence, by design, H3 is a parity check matrix for a Hamming code of length 13, dimension 10, and distance 3. I'll next make some notes about general Hamming codes. As I mentioned earlier, for every non-zero vector of length r over G of q, exactly one non-zero scalar multiple of v must be a column of a PCM for the Hamming code of order r over G of q. This is because there are q to the r minus 1 over q minus 1 columns in HR. And that's also the number of non-zero vectors of length r over G of q, up to multiplication by a non-zero scalar. Secondly, the matrix HR has rank r. And that's because among the columns of HR are scalar multiples of the unit vectors. In the example, we had the 3 unit vectors as the first 3 columns of HR. In general, we could have had any of these columns or non-zero scalar multiples of them in a PCM for the Hamming code. So this confirms that a Hamming code of order r over G of q indeed has dimension n minus r. Lastly, by design, a Hamming code of order r over G of q has distance at least 3. Moreover, among the columns of HR are the first 2 unit vectors, or non-zero scalar multiples of them, and the weight 2 vector with 1s in its first 2 coordinate positions, or a scalar multiple of this vector. These 3 vectors are linearly dependent, and so the smallest number of columns in a PCM for a Hamming code that are linearly dependent over G of q is 3. And so all Hamming codes have distance exactly 3. Therefore, all Hamming codes are single error correcting codes.
Hamming codes are commonly used in memory chips, such as DRAM chips, to correct random bit errors. These random bit errors occur in practice because of background radiation, mainly from cosmic rays. These cosmic rays might change the contents of one or more memory cells, or interfere with the circuitry used to read or write to them. The error rates increase with rising altitude, and so are significantly higher in aircraft and satellites. You can find more details about the use of Hamming codes in memory chips in the Wikipedia article entitled ECC Memory. ECC stands for Error Correcting Codes.
Let's design a decoding algorithm for single error correcting codes. By a single error correcting code, I mean a code with distance at least 3. And this includes all the Hamming codes since they have distance exactly 3. So we'll let H be a PCM for an NK code C over F with distance at least 3. Here's a definition we'll use throughout the course. Suppose that a code with C is transmitted and the vector R is received. Note that the received word has length n, which is the same as the length of the code word. Then the error vector is defined to be E, which is R minus C. Or equivalently, R equals C plus E. For example, if C is this vector of length 6 over Z3, and the error vector is 0, 2, 0, 0, 0, 0, then the received vector is 1, 2, 0, 1, 0, 1. Note that E has only one non-zero entry, namely its second entry. and so R differs from C in exactly one coordinate position. In general, the weight of the error vector is equal to the distance between the transmitted code word and the received word. So now, the channel decoder receives a vector R, but it doesn't know the transmitted code word, and of course, it doesn't know the error vector. So how does the channel decoder determine what the error vector was? Let's make some key observations. The main one is that H times R transpose can be written as H times C plus E transpose, which is HC transpose plus HE transpose. Now, since C is a code word, H times C transpose is 0. And hence, H times R transpose equals H times E transpose. This is nice because a channel decoder can compute H times E transpose without knowing the error vector E. And that's because it computes H times E transpose as H times R transpose, and the channel decoder knows the PCM H and the received vector R. So how can the channel decoder use its knowledge of H times E transpose to recover the error vector E? Now, the code C is a single error correcting code. And so, with the I-MELD decoding strategy, the decoder is only guaranteed to make the correct decision if the error vector has weight 0 or 1. If the error vector has weight 2 or more, the channel decoder might well make the wrong decision, and we don't care if that happens. So the job of the decoding algorithm is to decide whether the error vector has weight 0 or 1, and if so, determine the error vector. And it does this by examining the vector H times E transpose, which it computes as H times R transpose. Let's make some more observations. If the error vector has weight 0, in other words, it's a 0 vector, then H times E transpose equals 0. Of course, the converse statement isn't true. If the error vector has weight 1, let's say E is this vector with a non-zero element alpha in its ith coordinate position, then H times E transpose is alpha times the ith column of H. Since the ith column of H is non-zero, such a vector can be distinguished from the 0 vector. Also, since no two columns of H are scalar multiples of each other, we can distinguish the vectors H times E transpose when the non-zero entry of the error vector is in position I, from when the non-zero entry in the error vector is in position J, for any J different from I. So the vectors H times E transpose are different for each error vector E of weight at most 1. And this is the basis for the decoding algorithm. We'll make similar observations in the remainder of the course when designing decoding algorithms for linear codes which have error correcting capability greater than 1. Here's the decoding algorithm for single error correcting codes. The channel decoder is given a PCM for the code and a received word R. It first computes the vector S as H times R transpose. Recall that H times R transpose is also equal to H times E transpose, where E is the unknown error vector. The decoder checks if S equals 0. If that is the case, then it accepts R as a transmitted word. In other words, it declares the error vector to be 0, and it stops. If S is non-zero, then the decoder compares S to the columns of H. If S is alpha times the ith column of H for some I, then the decoder sets the error vector to be the vector which has alpha in the ith position and zeros elsewhere. and it decodes R to R minus E and stops. Otherwise, the decoder reports that more than one error has occurred, and error correction is not possible. By the observations we made on the previous slide, we can conclude that if the error vector indeed has weight 0 or weight 1, then the decoding algorithm is guaranteed to make the correct decision. On the other hand, if the error vector has weight greater than 1, then either the algorithm makes an incorrect decision, or it correctly reports that more than one error has occurred and error correction is not possible. Here's an example. So recall that we had the 743 binary Hamming code with PCM given by this 3x7 matrix. I'll remind you again that this matrix has non-zero columns and no two are equal to each other. Suppose that the received vector is this one. The decoding algorithm computes S equals H times R transpose and gets the vector 0, 1, 1. This is the sixth column of H. So the decoding algorithm declares that the error vector is a unit vector with a 1 in its sixth position and decodes R to R minus E by flipping the sixth bit of R. The result is this code word C. As a check, you can verify that H times C transpose is 0, which confirms that C is indeed a code word.
Next, we'll introduce perfect codes and see that Hamming codes are examples of perfect codes. Have a nice day.